Hello and welcome to online lecture number 9 for Chemistry 1101 during the spring semester of 2020. We are still in chapter 9, and in this lesson, we'll look at molarity as a conversion factor. In other words, we'll be given the molarity of a solution, and then we'll use that molarity to help us better understand something about that solution. So molarity, recall, is the ratio of the number of moles of solute per liter of solution. It's a unit of concentration, and it's the most common way in chemistry we describe the concentration of a solution because it uses moles as the way of expressing how much solute you actually have, which is how we normally count atoms and molecules in chemistry. In this first example, we're asked to calculate how many liters of a solution are required to obtain 0.234 moles of KCl from a labeled 1.25 molar KCl solution. So our picture may look like this, where we were provided a 1.25 molar KCl solution, and for a particular experiment, perhaps, we need 0.234 moles of KCl. The question is, and it's a very practical question, is how many liters of the solution do we need to give us this amount of solute? So ultimately, we want to relate our moles of solute, 0.234 moles of solute, is equal to how many liters of solution. So the unit conversion I need to make would be from moles of solute to liters of solution. And we're given the molarity. So let's think for a moment what molarity means. So molarity, 1.25 molar in this case, KCl, means that this solution was prepared such that there were 1.25 moles of KCl dissolved per liter of solution. So that's the ratio, that's the composition of this mixture. Composition of the solution is 1.25 moles of KCl, the amount of solute per liter of solution, per volume of solution. So because we're given this number, that means that this ratio will allow us to relate moles of solute to liter solution or liter solution to moles of solute. And that's going to be a general plan we'll see in today's lesson, is that anytime we need to go from moles of solute to liters of solution, or vice versa, then our conversion factor will always be the provided molarity. Because for this solution, in this case, what this means is that for the solution, 1.25 moles of KCl is equivalent to, in the context of the solution, 1 liter of solution. In the same sense that 1,000 milliliters equals 1 liter, or 16 ounces equals 1 pound. All those relationships are true, and in the context of the solution, this relationship is also true. So we can use this information as a conversion factor to relate moles of solute to liter solution, as we'll do here, or as we'll see later, liter solution to moles of solute. Molarity will be our conversion factor. So when we set it up, we have 0.234 moles of KCl is where we start. We want to use molarity as our one and only, in this case, conversion factor. And we set up this conversion factor, we set this ratio the same way we set up ratios, these conversion factors, in all our dimensional analysis problems, and that is we set them up such that the units we want to get rid of will cancel. So we start with moles on top, it means moles has to go on the bottom in order for those units to cancel. And what we're left with are liters of solution. So we want to have liters on top, and then we just add the numbers. So the molarity says that for every 1 liter of solution, we have 1.25 moles of KCl. So practically, to convert from moles to liters of moles of solid liter solution, I'm going to divide by the molarity. So 0.234 divided by 1.25 gives me a volume of 0.187 liters of this solution. So that tells me that in order for me to get 0.234 moles of KCl from the solution, I'll need to take 0.187 liters of the solution, and then that 0.187 liters, it consists of 0.234 moles of KCl. that's what that 1.25 molar concentration unit tells me, is that that ratio of moles to liters will be 1.25 moles per liter. So this is one example, and a very common example, as we'll see in today's lesson, of calculating, for example, the volume of solution we need to give us so many moles of the solute. Our second question is similar, in that we're given a 1.85 molar magnesium sulfate solution. For example, for experiment, we might need 3.10 moles of magnesium sulfate. And the question is then, how many milliliters of this 1.85 molar magnesium sulfate solution do I need to provide me with the 3.10 moles of magnesium sulfate? So as we'll see, very similar setup to what we saw on the previous example, except just one additional step. So this is our picture. So ultimately what we want to do is go from moles of magnesium sulfate. We want to go from moles of the solute to volume, in this case milliliters of solution. So ultimately we want to relate moles of solute to volume of solution. We can do so using molarity, because molarity is that ratio of moles of solute to liters of solution. So our plan, our strategy, is to start with moles of solute. We always want to build off on what we already know, already learned. If I have moles of solute and I have molarity, like we saw in the previous problem, I can always convert from moles of solute to liters of solution. That's what the molarity number is going to allow me to do. And then once I have liters of solution, the question asking for milliliters, I can then convert to milliliter solution using what I know about the relationship between liters and milliliters. So when we set it up, we have 3.10 moles of magnesium sulfate. It's a two-step conversion. First conversion, like in the first example, is that I want to use molarity as my conversion factor. So my molarity is 1.85 molar magnesium sulfate. So this tells me that in this solution, a 1.85 molar magnesium sulfate solution means that there are 1.85 moles of magnesium sulfate per liter of solution. So this might be my ratio I might need, either in this form or flipped, in order to convert from moles to liters. So I want to have moles in the bottom. So 1.85 moles of magnesium sulfate in the denominator. Numerator is 1 liter. So as we did before, divide by the molarity, go from moles to liters. But then the questions ask for milliliters. So then the second step is convert from liters into milliliters using the fact that 1,000 milliliters in a liter. So I'm going to first take 3.10 times 1,000 and then divide by 1.85, divide by 1, gives me a volume. My calculator tells me it's 1,676 milliliters to 3-cent figures. We can write it a couple different ways. We could write it as 1,680 milliliters, or it's probably better to write in standard notation as 1.68 times 10 to the third milliliters. So that's the volume in milliliters of this solution that I need to provide me with 3.10 moles of magnesium sulfate. So in these first two examples, we're both asked to calculate what volume of this given solution with a given molarity do we need to give us so many moles of the solute. Okay, this next question is a little bit different. It's a very practical question though, is that for experiment, for example, I might need a 0.7 molar potassium nitrate solution, and I might need 0.25 liters of that 0.7 molar potassium nitrate solution. And practically then I need to know how many grams or what amount of the solute, in this case grams of potassium nitrate, do I need to dissolve in this total volume solution to give me to produce this 0.7 molar potassium nitrate solution. So this is kind of our picture where we want to make a 0.7 molar solution of potassium nitrate. We want to make this volume of that solution. So the question is, how many grams of potassium nitrate will I actually need? So it boils down to that we have a volume of 0.250 liters. The question is then, how many grams of this solute do I actually need? And I'm given the molarity. For this class, anytime you're given the molarity, that means that you'll need to use that molarity as a conversion factor at some point to either relate moles of solute to liters of solution, or vice versa, liters of solution to moles of solute. So at some point in our strategy, we'll need to relate moles to liters or liters to moles, and that's going to be our molarity conversion factor. So kind of keeping that in mind, because a 0.7 molar solution that we're given, or we need to prepare potassium nitrate, means that the solution is to be prepared such that we have 0.7 moles of potassium nitrate per liter of solution. So that'll be the ratio we'll use to at some point relate moles of potassium nitrate, liter solution, or vice versa. So our strategy, our plan, is that we want to start with the volume, liters of solution. I know because I'm given molarity, I can convert liters of solution into moles of solute, in this case, moles of potassium nitrate. And then notice at this point, so this is what we've already been doing. Notice at this point where I need to go from here. The question is, how many grams of potassium nitrate do we need? So in one step, I can go from liter solution to moles of potassium nitrate. To get to grams of potassium nitrate, we use the same conversion factor we've used all along. Anytime we need to go from grams of substance to moles of a substance, or moles of the substance to grams of substance, that conversion factor is always the same. It's always the molar mass of potassium nitrate. So that's our setup. We'll start with volume solution. One step, convert to moles potassium nitrate. And then second step, use the molar mass of potassium nitrate, convert to grams. So we have two-step conversion. So we have liters of solution, 0.250 liters of solution. So 0.7 moles potassium nitrate over 1 liter of solution. So notice to convert from liters of solution to moles of solute, we'll multiply the volume in liters by the molarity. And then to convert from moles to grams, we'll need the molar mass. So quickly calculate the molar mass of potassium nitrate will be equal to the mass of potassium, 39.1, plus the mass of nitrogen, 14.01, plus 3 times the mass of oxygen, 3 times 16, gives a total of 101.11 grams per mole. So notice all the units cancel except for grams of potassium nitrate. So we have 0.250 times 0.7 times 101.11 gives us a number of 17.7 grams of potassium nitrate. This calculation tells me, this is very practical, is that in order to prepare 0.25 liters of a 0.7 molar potassium nitrate solution, I need to dissolve 17.7 grams in that total volume of solution. And that, once it's fully dissolved and homogeneous, then that will give me my desired 0.7 molar potassium nitrate solution. And finally, our last example today is we want to calculate what volume in milliliters of a 0.45 molar lithium chloride solution do we need to give us so many grams, in this case 10 grams of the solute lithium chloride. So this is our picture. We want to relate, or calculate rather, the volume of this solution. How much of the solution do we need, of this 0.45 molar lithium chloride solution do we need to give us 10 grams of lithium chloride? So notice we're given the molarity. So as I said in the previous example, at some point we need to use that molarity, use that number to relate moles of solute to liter solution, or vice versa, because a 0.45 molar lithium chloride solution means, and I think it's helpful to actually take this capital M and rewrite it based upon its definition, which says that 0.45 molar lithium chloride solution is a solution prepared such that we have 0.45 moles lithium chloride dissolved per liter of solution. That way it's already in that ratio, and as we've done almost from the very beginning of the semester, when we see ratios, we almost always use ratios as a conversion factor, and this will be no exception. We'll need to use this ratio at some point to relate moles of lithium chloride to liter solution, or liter solution to moles of lithium chloride. So in our plan, our overall plan here is we want to relate grams, in this case, 10 grams of lithium chloride. That's how much lithium chloride we need for an experiment. And we want to calculate how many milliliters of solution do I need, in which there will be 10 grams of lithium chloride. So we'll start with our 10 grams of lithium chloride. And we may not necessarily know where to go from here, but we know that we're given molarity and we're asked about volume of solution. So sometimes it helps to kind of start where you can, but if you hit a roadblock, it sometimes helps to go to the very end of the plan as well and kind of maybe work your way backwards. So we know in the end that we want milliliters of solution. And I know that I can get milliliters of solution if I'm able to calculate liters of solution, because I know liters and milliliters, what that relationship is, as we've seen previously. And because I'm given molarity, molarity is always going to allow me to relate moles of solute to liters of solution. So I can get liters of solution from the given molarity if I'm somehow able to determine the moles of lithium chloride. And then the missing puzzle piece comes in place. Grams and moles, we know how to do that with molar mass. So this is the most complicated of these types of calculations. Grams and moles using molar mass information, moles of solute to liters of solution using the molarity information given to us, and then finally a unit conversion, liters solution to milliliter solution. The first step is to convert from grams of lithium chloride to moles of lithium chloride. So to do that, we use the molar mass of lithium chloride. So we'll divide by the molar mass, as we've done many times before. So the molar mass of lithium chloride is the mass of lithium, 6.94, plus the mass of chlorine, 35.45, for a total of 42.39. That allows us to convert from grams and moles. To go from moles to liters, I'll use my molarity. And so my given molarity is 0.45 moles of lithium chloride per liter. So I want to convert from mole units. So mole units go on the bottom with its number. 0.45 moles of lithium chloride per liter of solution. And finally, convert from liter solution to milliliter solution using our definition of liters and milliliters. There are 1,000 milliliters of anything in 1 liter, the same thing. So our overall calculation is 10 grams, 10 times 1 times 1 times 1,000, divided by 42.39, divided by 0.45, says that I need to have approximately 524 milliliters of solution. So if my question is to determine what volume of this solution do I need to give me 10 grams of lithium chloride, I'll need about 524 milliliters of that solution. Because in 524 milliliters of a 0.45 mole lithium chloride solution, I have enough moles of lithium chloride to equate to 10 grams of lithium chloride. So we've seen in today's lesson how we can use molarity, a given molarity, in all these examples at some point to relate moles of solute to liter solution or liter solution to moles of solute. So at some point, in other words, when you use that molarity as a conversion factor, it may be the only conversion factor we need, and maybe just one of several, but at some point we need to use that number as a conversion factor. Now that we understand how to test the concentration of solutions, what good is that? What does that allow us to then predict about the behaviors of these solutions?